So we will now study about random variables. So what are random variables? The name, by name, we can think it's a variable, but it is in fact a function. So the way it is defined is, it's a function from sample space to the real line. So we can write it as x such that it is from capital omega to real line. So what it means that it takes an element from omega. So what is an element in omega? It's an outcome. So it takes an outcome, maps to it a number. So for every outcome small omega, x omega is a real number. It can be positive, negative, anything. And this provides you a way to numerically map outcomes to some number. So for example, let us see this. Suppose capital omega represents a coin toss. So it is made of two outcomes, h and t. If I want to define a function over this omega, I have to define it for every element of this capital omega. So I will say that for h, the function maps to 1, and for t, the function value is 2. Okay, recall the function definition is that if you want to define a function, you have to map every element of the domain to a unique element. So as xh is 1 and st is 2. One element should not be mapped to two numbers. So we have just defined these things. So basically, random variable is this one, right? And why do we need such a function? The thing is, outcomes are a physical phenomena. To be able to do some maths over this, to understand them, how they occur, we need to put some mathematical framework around it. And that the random variable is one way to do this, that you take outcomes and map to a number. So now instead of outcomes, we have a set of numbers, one for each outcome. So is this all which is there for random variables? No, there is a small extra condition which need to be also satisfied for a function x to be a random variable. So for that, let us understand this. Suppose x is a function from omega to r. And of course, if there is an omega, we have defined a sigma algebra f, which contains all nice, interesting events. Similarly, on R, there is a sigma algebra, Borel sigma algebra. And we know that omega f are measurable space, and also R and Borel algebra, this pair is also a measurable space. Right? Remember the definition of measurable space, that if you have a sigma algebra, the omega f are known as a measurable space. And every element in F is known as the measurable set. So here all elements in F are measurable, and here also all elements in this Borel algebra are measurable. Now let us consider this particular example. This is your lambda omega, which has 4 elements, and this is the real line, and this omega is mapped to these 3 values. So this first element is mapped to this one, the second is mapped to this element, third is also mapped to the same element, and fourth is mapped to the last element. So this is a valid function. Now let us recall the definition of pre-image. So if I take a set A here, right, remember the set in the real line is like an interval or the union of countable union of intervals. So if you take any set here, specifically if you take any Borel set here, and you try to find an image of this here, so what will you get? Sorry, pre-image of this, what will you get? So remember, what is the definition of pre-image? A pre-image of a set B under X is given by, which we denote as X inverse B, is given by all omegas such that X omega is in B. Okay, so if you are given a B which is made from some elements, you try to find out all elements which map to one of these elements in B. and you collect all those elements which map to one element in B, and that will be your pre-image. So formally, I said that pre-image is made from all omega such that X omega is in B. And some elements of B can be left, that is fine. But there should not be any element which is mapping to the element in B but still left out. So you have to make it, you have to include all the elements, all the outcomes. And you can recall that no matter what B you take, if you take X inverse B, it is made from some outcomes. Okay, so it will be a set of outcomes. And what is a set of outcome? It is a event. Okay, set of outcome is an event. So for every B, X inverse B is an event. Right. And what we want here is that it is an event, but it should be in the sigma algebra. Why do we want that? Because remember, we have defined the probability measure on every element of F. Okay, that is why the reason we made this sigma algebra, that we defined the probability measure on every element of F, every event in F. But we did not define it for every subset of omega. If sigma algebra is smaller than the power set of omega, there may be some subsets of capital omega which we have not defined probability measure. What we said that F contains all interesting events and we will define probability measure on that also only. So if you somehow comes to a case where your X inverse B does not lie in F, right, then what you get is a subset on which the probability measure is not defined. Okay, and that will create some problem which we'll see as we move ahead, right? So let us see this. So I will define measurable function first. What is a measurable function? If omega F is a measurable space, means F is a F is set and F is omega, capital omega is a set and F is a sigma algebra on this. Then we say a function F from omega to real line is said to be a F measurable function if for every Borel set B, F inverse B is an element of F. Okay, so let us understand this. Why we are saying Borel set B? Because our codomain is real line. So what is the sigma algebra on that? That's a Borel algebra. So any element of that Borel algebra. Okay, recall any element of the Borel algebra is measurable. And we call it a Borel set. So if you take any such element, any such Borel set, then the pre-image of it under F should be inside F. It means if we take a set B and try to find out all outcomes which maps to an element inside this set, then the collection of these outcomes should be in F. Okay, which means it should be measurable set. So in other words, we can say if the pre-image of every Borel set B is F measurable, remember what is F measurable? That it should be in F. Then we say that function is a F measurable function. Okay, and remember for this particular case, when omega, capital omega is a sample space, then F inverse B is an event. Okay, so our goal is that if we force that F is also F measurable, then we will force that F inverse B, which is an event, is in F, is in capital F, is in sigma algebra F for every possible Borel set. Okay, so our goal here is in defining such function is that every interesting set in real line. Okay, why we are saying every interesting set? Because we already said that in real line we have a Borel algebra. Borel algebra is made from we say that it's made from interesting sets, and it is actually made from Borel sets. It means we are saying that Borel sets are interesting sets for us. What are these interesting sets? They can be open intervals, closed intervals. We are generally interested in such kind of sets. So what we want is, once we define the random variable f, then every interesting event in the real line can be mapped back under this f to a interesting event in f. Okay, or measurable event in f. Okay, if it is outside sigma algebra f, then we do not know how to measure it, because remember, we have defined a probability measure in probability space, and the probability measure only measures set in which are available in sigma algebra f. It is not defined for rest subsets of capital omega if there are. So we want to just make sure that no matter what f you take, you should be able to find map every interesting event in the real line to a measurable function in outcome space, sample space. So the formal definition would be a function x from omega to r is a random variable if f inverse b is f measurable. In other words, for every Borel set, f inverse b should be in the sigma algebra of omega. Okay. So let us take this case. Sorry. So you can understand, if sigma algebra does contain every possible subsets of capital omega, then you don't have to worry, because no matter what you pre-image you take, it will be one subset of capital omega. Okay, see, the function is mapped from capital omega to R. So no matter what set you take in the Borel algebra, if you try to find map, it's made from some outcomes. So it will be a subset of capital omega. And if you have taken a sigma algebra f which contains all subsets of omega, then this will of course be in f. Okay, so then you don't have to worry. But if your sigma algebra is smaller, then you have to make sure that your pre-image should be in sigma algebra. So let us see an example here. Suppose there is an experiment of tossing a coin. So your sample space is h comma t, and you have defined a particular random variable. Let's say for now it's a function from omega to r, such that h is mapped to 1 and t is mapped to 2. Okay. So remember, both can be mapped to same number. That is a function. That's not a problem. But h cannot be mapped to two numbers. In a function, every element of domain should be mapped to one element only. So we have defined here as a separate, different values for each outcome. Sh is 1 and xt is 2. Okay. Again, remember, this random variable is a function of outcomes, not events. So to be able to fully define it, you need to just define it for every possible outcomes of omega. So prove that for every Borel set, the pre-image is measurable. Okay. Now, if you to be able to say that it's a random variable, you have to take every Borel set possible and find the pre-image which is measurable, right? And that becomes a tedious task, because there are many infinite elements in the Borel algebra of real line. Okay, so there is a shortcut available to us, which we say that if you take Borel sets of the following form, which is minus infinity to x, which are closed from x. So these are semi-open intervals, which are intervals containing all real numbers from minus infinity to x, including x. Okay, and this x is can be any number. So you take different x and you can get different bx, which are in this form. And if you can show that for every bx, for every x, the pre-image of these sets bx is in f, then that's a sufficient condition. You don't have to prove all countable unions or every possible interval that this is in pre-image is in f. You have to only prove that for these particular types of sets, which are semi-open from infinity to x, for all possible values of x, the pre-image of every such set is in f. And if you can prove that, that is sufficient. And it is a little bit easier to show that. We will see one example. So for this case, we have considered, let's take sigma algebra for omega as the complete power set. So F is phi, H, T, and HT. Okay. Of course, in this case, it will be a random variable because they are taking the complete set. But for just for a demonstration purpose, how do we calculate the pre-image of Bx for every x? I have taken this example. Okay, and you can do the same process for any random variable, and then whatever result you get for every x, you have to just make sure that those sets are in F. So let us see. Let's take one by one. If x is a number smaller than 1, so let's take the number is minus 10. Okay, so the bx would be minus infinity to minus 10. Okay, so you have to find the pre-image of this. So pre-image means you have to find all outcomes which map to a number in this set bx. And the number is, this set is made from all numbers between minus infinity to minus 10. So what are the outcomes which map to one element in bx? So there are only two outcomes. One is mapped to 1 and another is mapped to 2. None of them maps to any element between minus infinity and minus 10. So the pre-image will be empty because there is no such outcomes which maps to this set. Okay. So the x inverse bx would be phi. Is phi in F? Yes, it is in F. Let's take, so you can take anything like minus 100, or so I have not written all those things, but you can take minus 200, minus 10, anything, any negative number or even 0, there you will get 5. Okay, so if you take minus 0.99, 0.99 also, there's no number which maps, which is less than 0.99, so you get 5. Now if you take 1, then you have to find all numbers which maps to any number between minus infinity and sorry, not minus 1, 1. So you have to find out all elements which maps to any number between minus infinity and 1. So in that case, uh, uh, what are the outcomes which maps to a number between minus infinity and 1? So H is that outcome because as H maps to 1, which is included in this set. Remember, this is a closed set from 1. So 1 is included in this set. So X inverse Bx is nothing but H, which is also in sigma algebra. If you take 1.2, 1.3, you get the same answer. If you take 1.99, this also includes 1. Okay, but does not include 2. So the pre-image is also H. Now, if you take 2, then Bx is minus 22. So this all includes 1 and 2 both. So what are the outcomes which maps to any element in this? H maps to 1, T maps to 2, both are in this set. So the pre-image includes both these outcomes. The pre-image is H comma T, which is capital omega. And if you take a number bigger than 2, like 2.01 and 2.3, then also it contains both numbers and its pre-image will be capital omega. So we can say this, that x inverse of this set minus 22x is phi if x is less than 1. It is H, set H, if x is between 1 and 2, less than 2, greater than 1, greater than or equal to 1. And it is omega if x is greater than or equal to 2. So for every possible x, we have found what will be the value of x inverse. And then we said for every x, these are in F. So this will be a random. This will be a sigma algebra. Okay. So you can understand this if we have taken this random variable, but our sigma algebra was just phi and omega. Right? That's a valid sigma algebra. Then this will not be a random variable. Why? Because for some x, you are getting a set H, which is not in the sigma algebra. Okay, so this is the procedure you have to apply when you have to calculate whether the given random variable is, given function is a random variable or not, right? Just first you have to make sure it's a valid function. Okay, Function I have already covered, so just make sure it's a valid function. Make sure all the elements of all the elements of domain are covered. It is defined for every element in the domain. And you have to just make sure that no matter what no matter what x we take, minus infinity to x pre-image should be in sigma. Now we will see one example to understand what is random variable and why do we need them. So let's take a simple example. There is a ball full of candies, and then you want to pick one of the candy. That is our random experiment. So random experiment is to pick a candy or marble, whatever. So your outcome would be, each outcome would be that you picked a particular candy. So let's say suppose there are 16 candies, okay? And each of you are unique candies. You can number them or you can do some marks to understand. So each of this picking of each candy would be one outcome. So a sample space, if you want to understand, if I make this square, it will be divided into 16 outcomes. Okay, each denote picking of a particular candy. Okay, so these are 16. There will be 16 candies. Now you can look at this. Each capital omega denotes. So you can say omega 1, omega 2, omega 3, omega 4 like this, and each omega I would make that you have picked. The outcome is that you have picked a particular ith candy. Okay. Now thing is, see these events, picking of ith candy, or even if you don't number them, they are picking a particular candy, right? Like picking a Cadbury chocolate or something like this. So the question is, these are all physical phenomena, and there is no mathematical framework to that, right? There's nothing, no numbers assigned to it. So how do we write these omegas? How do we do any maths or engineering over this, right? We know that for any engineering application, we need to write it in a well understood mathematical framework. So to be able to convert this to a framework, that is where we need random variables, right? So let's see. Suppose we are picking a candy, right? Uh, but we cannot. That's a physical event. It's a physical phenomenon. So, or suppose we pick a candy or a machine picks a candy. It picks it up, right? Yeah. Let's understand. A machine picks a candy, right? Now, machine tells you what it has picked. So, of course, machine cannot describe the phenomena in complete what has occurred. It gives you some kind of indicators, right? For example, it can pick a candy and tell you what is the color of it. Okay, so you'd perform this random experiment, and what you observed is a variable which can be red, blue, green. Okay, so think that there is a big machine. It picks a candy from the ball and then display on a screen the color of it. So whatever it is displayed, let's call that X. Okay, and let's make it number. Suppose red is 1, blue is 2, and 3. So if it displays 1, it means it has picked a candy which is red. It has, which is 2, it has picked a candy blue, and if there is 3, it has picked a candy of color green. Okay, right. So this is one. If you want to understand this, this is X is a random variable here, right? How? Basically, it takes one outcome and it look at the color of that candy and just displays the color of that candy. It cannot tell if there are two candies of the red color. It will tell just red one, right? It doesn't distinguish between these two candies. For it they are same. right? So what it is doing that, it is taking each of these outcomes here, okay, and looking at its color and mapping to a number, okay. So if this is candy is 1, suppose there are 3 values, 1, 2, 3. If the candy is this, it maps to 1. If this candy, suppose second candy is green, it maps to 3. Okay. Suppose this candy, third candy is also red, it maps to 1. So what we are seeing here is in this particular experiment, the machine is not exactly able to tell the exact what candy it has picked, but instead gives you some information about the event candy, right? So it tells you the color of it. So what does it actually doing in this process, underlying process, that it takes each outcome and map it to some number, which is done in a way that this number here represents the color of the candy. So every outcome is mapped to one of these 3 numbers. Okay. So if you finally draw it, they all will map to one of these numbers. Right. And here when you observe this x is actually a function of omega, because depending on what outcome actually has occurred, this value would change. If this outcome has occurred, you will see x as 1. If this outcome has occurred, you will see the value as 3. Okay. So when you look at this machine, you will observe one of the variable 1, 2, or 3. Right? Instead of looking at actually candy, you will just see one of the number 1, 2, 3, and that somehow denotes the outcome. At least you will be able to tell that if 1 has occurred, only those numbers will occur where the outcome is, where the candy is red, right? So you have some information about what candy may have been picked, although you don't exactly know the exact, you don't know the exact outcome, right? But these outcomes are mapped, and one in this way you have seen. So this X, which shows the color of the picked candy, is a function of the outcome. Okay, because picking a candy is a outcome, and looking at the color of it is a function of outcome. So this X is a function of outcome, and this is what random variable is. That instead of dealing with this outcome, 16 outcomes with a physical phenomena, which we is hard to do in mathematical framework, we now have a very simple line, a very simple format, which is just a integer, a number. Right. What other can be another map, right? Suppose the candy is packed, right? So the machine cannot see the color. But what it can do is it can pick its, uh, it can scan its wrapper and can know the company name, right? In that case, suppose there are Amul and Cadbury. So the company here displays the brand of the candy. So it says either Amul, which we, let's say Amul is 1, and if it's Cadbury, it displays 2. So this is also a map of the outcome, right? So every outcome it takes, which is picking of a candy, it looks at that candy and find out the company name and displays accordingly. So Y is also a map, a function of uh, which of outcomes. It takes one outcome and it's a color, sorry, is the company name it denotes. And whenever you look at this machine, when it performs one outcome, it displays only one of these 2 numbers. Okay, depending on what it has picked. Here also, in this case also, it only picks one of these number, right? So when I look at the variable x, I see one number, right? And if you repeat the experiment, you may see a different number, right? So that is what is happening here, that this x looks like a random thing, right? Whenever a outcome happens, you may see a different value of uh, this variable, right? What in mathematically we can see that it's as a function, right? To define this, we will just define a function that for every outcome there is one value of x, right? And when the random experiment happens, one of the outcome occurs, so that is why there is one value of x is what we got. right? And sometimes we also call it sample, right? That when you do this outcome, you got one sample of X, okay? And the value of that is called, is the sample of X, okay? Similarly, when you do this, suppose I got one, so I will say one is the sample of Y here. Okay, if I do it multiple times, I will get different samples, right? I will get a sequence like 1, 2, 1, 1, 2. This is the sequence of saying that first is the Amul, second is the Cadbury, Amul, Amul, Cadbury, like this. Okay, so now you may understand that actually this X denotes some information about what outcome has occurred, right? When I look at the value of X, I may know what outcome has occurred. It gives me some value, right? So this can be like you are doing some experiment and the machine just displays the signals or display one value, right? That is related to the outcome. So you cannot see what outcome has occurred, but you can see exactly one value which is direct, is a function of outcome. Okay, so if different outcome has occurred, we will see a different value. But you cannot actually observe the outcome. You can only observe a function of the outcome, right? There are many things like this happen, right? When you operate a machinery, there's a lot of random processes, random things are going on this machine. You cannot observe everything. But if you try to plot the signal, you may see some noise. So that noise is an outcome of the complete random experiment which is going on in the machine. Okay. So this is what a random variable is. Right. Now the next question is, what does the right? So what do we then proceed on this random variables, right? Why we have talked about this specific condition that the map should be such that the pre-image is measurable, right? Let's understand that. So we will take the same example. So let's see. So this was our omega, okay, which was made here of 16 different outcomes. Okay, so these are elements of the different elements. Each one is a omega I, omega 1, omega 2, omega 3, like this. And these are how complete omega is made. Right. Now we said that we want to understand the probability of each subset of omega, right? What is the probability that a particular outcome has occurred, or what is the probability that one of the two outcome has occurred? So I can take any set in this, and I would like to know the probability of that, right? So this is one set, this is another set, right? All this thing. I want the probability of that, right? So if I want to know the probability of this, it's here in this case, the discrete probability space. So I can just add this subsets. I'll get the probability of the complete subsets. So what I do is here, I make a list of all the possible subsets I want. So this is one subset, I write it here. This is another subset. Let's call it W1. So this is W1. This is another subset. So this is another subset W2. This is another subset, which we also write here. Okay, let's call it, suppose this is W8. So this is W8. Similarly, you will write all 16, right? Then of course, this is also a subset. So you write down all those subsets and all possible combination, which will be 2 to the power 16 here. Those will be, if you make a list of that, that will be sigma algebra, right? And when I have to define the probability measure, right? If I take, I have to assign probability to each of these elements in F. So first I start with the singleton events. I take this and map to a number. This number denotes the probability of picking up this candy, right? Similarly, the second candy will be picked by 1 by 16. So outcome is event that you have picked the second candy is 1 by 16, right? I'm assuming equally probable case, but of course this depending on the machine algorithm or mechanism, this may have different, like one can be like 1 by 8, another can be small, something like this. Right? If they are big candidates, machine may have a higher chance to pick it, or machine may have some bias. Okay, so that is not our concern here. What is the exact probability? But there is some probability which is consistent with the actual physical phenomena, right? So once we have defined this, we have defined omega, Fn and P. This is our probability space. Now we say this is the underlying probability space which is there, which is actually related to physical phenomena. Now our question is, when machine picks it, I may not see all the outcomes. What I see is a particular number, right, which is the color of it, right? So when I look at this machine, I see when I look at this machine, I see one number. It can be 1, 2, or 3, which denote the color of this candy, right? So now our goal is, we have already defined this omega fp, right? I don't want to go and do the same probability again. What I want to understand it, if I know this probability space, can you tell me what is the probability that I will see a number 1 in this machine, or I see a number 2 or number 3 in this machine, right? Again, you can do the experiment and try to do it multiple times. And that is the actual physical meaning of this, that you look at this machine and see how many times out of, suppose you do 100 times, and how many times it has displayed 1. If it is 20 times, it means the probability is 20 by 100, right? So that is the interpretation of it, right? But once we know the actual phenomena, actual probability space, constructed on the actual physical sample space, then I would just want to connect them together, right? And they are connected, right? Because this acts as a map of outcomes. So there should be a consistent way to define the probability on this axis. Okay, so to be consistent again, if you look at this, uh, X now has 3 outcomes. If I look at this machine and think that observing the value of X is a random experiment, then you will get 3 outcomes. One is X is 1, second outcome is X equal to 2, and the third outcome is X equal to 3. Okay, so these are all numbers because random variables are numbers. So you get 3 values, 1, 2, and 3. These are your sample space. Actually, this line is your sample space, and you only get 2 values, 1, 2, and 3 in this case. Okay, so because sample space is a exhaustive list, what you get here is a just 3 number 1 to 3. Or I can also sometimes say the whole complete line is a sample space, and all the numbers except 1 to 3 just don't occur, right? So this way we get a uniform unified approach that our this new sample space is just the complete real line. Okay, of course it will be better to just say that omega here is actually just 1 comma 2 and 3 is a discrete space, right? Because only 2 3 things can happen. But to make it unified, I would say that the sample space is a real line which includes all number, but only 3 things occurs here, right? Only 3 numbers occurs, and the rest are have a probability of 0. Okay, so they are actually outcomes, but they never happen, right? This is just to make a unified thing, so that we don't have to redefine this omega dash for every new random variable. Okay, now we want to ask, right, what is the probability that X is equal to 1, right? So again, before even asking, so okay, let's understand what is X equal to 1, what is the probability, what is the physical meaning. I already said, we look at this machine, we just want to know, if I do this experiment 100 times, how many times I will see a 1 here, right? That is a frequency approach. But again, in all sense, probability means if I just do this randomly, what is the chance that I will see a 1 here? Okay, so again, before I even define the probability, I need a sample, I need a sigma algebra also in this. Okay, so it's a real line. So what will the sigma algebra? Sigma algebra will be the Borel set on this line. Okay, so every possible set, right? A list of every possible set on this line, sorry, not every possible set, all the sets of the form union and intersection of countable union intersection of open, closed and semi-open intervals, those will be in the sigma algebra. Okay. So let's not go to much detail on that, but we know that one of such set would be this set. Right. This is a line segment, which is a Borel sigma algebra, which is in the Borel sigma algebra. So it's a Borel set. I want to know what is the probability of that. Okay. What is the probability that X lies in this set? Okay. Now you have to understand this is an event, right? Why? Because this is made from outcomes that X can be this, X can be this, X can be this, X can be this, or this, all these numbers. Okay. So ideally, if you look at this, there is only one event which is actually have non-zero probability. Is this only one outcome is actually having non-zero probability? That is just one. Okay, but let us write this as 0.5, 1.5. Right. This is the a set. This is a Borel set in this Borel sigma algebra. And this means that X takes a value between these two, right? Now this is an event, right? Because this is a set of outcome. This is one outcome can be X is 0.5, one outcome is X is 0.6, one outcome is X equal to 1. So this is a set of different outcomes. Okay, so actually if you look at the outcomes who are picking up the candy, right? But you can also think that observing the X and getting different values of X is also an outcome, and they are actually linked random experiments, right? Picking up a candy and then you look at the color of it, that's a linked, these two are linked random experiments, right? That is why the outcomes are also mapped. If you pick a particular candy, you will see a particular color, right? So that is how when I say this is a event, because this actually represents a event, right? So this represents an event that X has become 1, right? Now, to write it more precisely, I would want to understand in omega, in the original capital omega sample space term, what omega this event includes, right? So the event that X, this event, this set is an event because made from many outcomes. I want to understand what outcomes this event represent. Okay, what? So here, this is just a number, right? It's a set. It's open interval. So how does this connect to the original sample space? Right? Very easy. So this represents when X takes a value between this, right? So let us look at all the outcomes here, right? Such that when they occur, X becomes this, right? So it means when that outcome happen, the machine displays X, right? So when will the machine displays X? When you pick any of the outcome here which are red, then you will see a value which is 1, right? And no other value in between 0.5 and 1.5 can occur, right? Machine can only display 1 in this set, or 2 and 3 which are not in this set. So this event can only occur, when machine picks a red candy, right? Let's understand, let's assume that yeah, let's assume this one, and this one. These three are red candies. Okay, so it means the set which is made from these three, right, the set which are made from these three, let's call it E. That set, this event, right? It's also an event because it's made from outcomes of picking this candy, and this candy, right? So when this outcome occurs, X becomes 1. When this outcome occurs, X also becomes 1. This outcome occurs, then also X becomes 1. So if any of the outcomes here occurs, this event will occur, right? And we know if any of the outcomes of a set occurs, then means that event has occurred, right? So if this is E, this set is E, then if any of the outcome here occurs, then we see E has occurred. So this E has occurred, and also from the previous argument we say when this occurs, this event will occur. So this means this event and this events are equivalent, right? So if this is let's call it as a M event, then this M and E are actually same, right? Just the way of writing is different. Here M is a open interval. Here E is a physical phenomena, right, which is made of three outcomes, which each of them is picking a particular candy. Okay, so now you can understand how they are connected, right? And the way to mathematically formulate this is by this way. You said that if you have any event in the Borel's, which any Borel set, you can say that find all omega such that their map lies in this set. Okay, so if I have a Borel set B and I want to find the equivalent event, I will say that this is equivalent of a set which is made from all omega such that x omega belongs to B. Okay, here also we see this event. We also all find all those candies. When they're picked, the machine displays that, right? So that display is a map of outcome. So this, if you look at, is nothing but the pre-image of B, right? That is why we say that finding all the outcomes which maps to this set, which maps as that the map image becomes part of this B set, is a pre-image of that, and that we write as X inverse B. Okay. So that is why I say if you have a Borel set and you want to find the equivalent event, you just look at the pre-image of that, right? If I ask you another question, if I am given a set E and you want to find what event, what will be the equivalent event in this new space of the machine observation, then that is very easy to get. You take each outcome, find it map. Here they map all to one, and that will be my image. Okay. Right. So that is what is here. Right. Now the next, okay, and the one part which also need to be understood here is that if you look any of the these outcomes, right? Let's take a bigger another set, which is this. It has 1 and 2, right? So if I want to find the equivalent event, means 1 and 2 has occurred. So I want to make sure that 1 has occurred, which means all outcomes where the candy is red, and a second would be all outcomes where the candy is blue. Okay, now you can understand when I change the X, I make it Y, right? The event totally change in the for the Y. Suppose it is the company name Amul and Cadbury. Then when I say this set, then it represents the picking of a candy which is of Amul company, right? And that's a different thing. That's a very different event, right? So here this pre-image depends on what is X. Even if you take the same the pre-image will change. Now coming back to the last part, that once we have the idea was we had a omega F and P, and what we found that we mathematically were able to observe a map of this sample space, a particular variable x omega, and we say that to make it unify, I have take the Borel algebra as a sigma algebra. Right. So our goal is to construct a new omega dash and Borel algebra, and of course a probability space, such that I don't have to so that I will also have an understanding how does this X happens. Okay. So one question would be, if I want to say no, what is the chance that X is 1? Okay, so that means if I'm looking at this machine, I want to know what is the chance that this machine will display 1. Okay, so I said that I to make it uniform, I take a real line. This is new omega dash, right? And I complete a sigma algebra. So all the possible intervals in this and are in the sigma algebra. Now I want to assign a probability, right? And this probability should be consistent with the original one. So this means when I say that if I take any Borel set here and I want to ask what is your probability of this event, right? This is an event and I want to ask what is the probability of that event, right? Then as I said, this event is an equivalent to an event here, which is the pre-image of that. Suppose this is event B, then this will be x inverse of B. So probability of this event should be equal to probability of this x inverse B. Okay, so that is just meaning that there is different way to say this. I want to say that probability that x belongs to B, right? Which means the event that what x is observed is one of the element in B, right? So this B has occurred, this event has occurred, B has occurred, or we say x is in B, or sometimes we denote this format. Px is the new probability measure on B, which says there's the size of the B, right? And this size is the probability the event has occurred, right? One way to say this also is this probability of all set omega says that x omega is in B. Okay, so this is the pre-image. This is on the original probability measure. Okay, and one last thing which we have to make sure that because we can take any of this so when I take this sigma algebra, I can take any of these events, right? Any of these events. And I just want to say that if I take any of the set and I tell that this is my probability, this means that I should be able to find so if you want the probability of B, you will just say that I need the probability of x inverse of B. Okay, and to be able to say that probability of some set, it means this is the original probability measure. This means this x inverse B should be in F. Okay, this should be true for all B. Then only you guarantee that they will be always probability, right? So to say that we have a valid probability measure, all you need is to make sure that this sigma uh, is a sorry, this random variable whatever it is, the pre-image of any Borel set always exists in F. Okay, and once we make sure, then we can guarantee that there will be always a probability measure. So now let us understand one example which is not a random variable. So although it's a function of the sample space. So let's take a particular case. Suppose there are 3 marbles in a ball and you want to pick one of them. And so these here what you can see is a omega, and you have here three different outcomes. So this denotes the picking of this marble, this denotes the picking of a orange but hexagonal one, and this picks up represents the picking of a green marble. So suppose the person is not interested in the shape, he's only interested in the color of the marble you have picked. So the way you can create a sigma algebra is by only considering those events which have different colors. So in that case, when you create a sigma algebra, uh, you this sigma algebra will consist of these 4 values. One is empty set, which does not have any marble. This includes the picking of a green marble. This includes picking up of a orange marble, and this is a complete omega because you have to include that as a condition on sigma algebra. So it has 4 elements in it. Okay, and this is a sigma algebra because you can prove that union and intersection also belongs to the sigma algebra. Okay, so this is based on our interest is only looking at the color. Now if I have to assign a random variable to this, okay, so now I have specifically picked this illustration and have not assigned any number or this thing, a string to represent the sigma algebra, just to make a point that at the base level, omega fp, these are still physical phenomena. They are not, may not be directly written in the math representations. So to be able to do any kind of mathematics over it, any kind of analysis on that, we have to convert it to numbers, right? And that is where random variables comes in picture. So we have three outcomes. One is picking of a first orange marble, second is picking of this hexagonal marble, and third is picking of a green round marble. Suppose someone says that I want to call it 1, this 2, and this 3. This is my x omega. Okay, so this function, this is all omegas, and this is the number you assign. So once you map this on real line, this will be 1, 2, 3. And suppose this is 0. So these are three numbers where these outcomes are mapped in. Now to be able to say that this is a random variable, we must make sure that every possible Borel set has a pre-image in the F. Okay, and why that is important will also be clear in few minutes. So you can see first, once I have defined omega and F, P would have only 4 values because it's a map from F to real line. So you will assign some number to this. You have to assign 0. Second, you have to assign some number to this. Let's call it 1/4, this as 3/4, and this as 1. This is your probability measure. Okay, it has 4 values. Now, if you ask me what is the probability measure of this set which only have one orange marble? Okay, we do not know the probability measure of this because it is not in F. We do not know. Only thing we know that probability of picking this or this is 3/4, but we do not know the individual probabilities of picking them up. They can be half of these or can be anything. We do not know. So once we have this, now let us see whether this is a random variable or not. So let's take this set. Right, this is a Borel set on real line. What is the pre-image of this? So this is the pre-image of would be all omega which maps to number 3. Okay, and only omega which maps to number 3 is this green marble, picking up this green marble. So your set will be this. The pre-image of this set is a thing which a green marble. This is green. Is this set belongs to F? Yes, this set belongs to F. So this is okay here. Let's take another set, which is this. So this, the pre-image will be all the outcomes which map to 1 and 2. And this will be this set, which is also in the sigma algebra. Now let's take this set. This is only includes 1, does not include 2 and 3. The pre-image of this would be outcomes which maps to any number in this set, and because 1 is the only number which can be in the range of random variable, so all outcomes which maps to this set, this maps to this set is just there is only one outcome. So I can, like, this is a orange picking up this orange marble. Okay, now is this in the sigma algebra? No, this is not in sigma algebra. Okay, so this is not a random variable. So question is why this is happening, because we have seen that we have taken 1 and 2 a different number. We have mapped this and this to a different number, right? 1 and 2. So we can always take a set around 1 and does not include 2. And once we do this, the pre-image will only contain one outcome mapping to 1. So in this case, when you pre-image will not be an F, because in sigma algebra these two are together. So what we can understand here what we can do here to make it random variable. First thing, we have to make sure that in sigma algebra does not distinguish between two orange marbles. It distinguishes between green and orange marbles, but it does not distinguish between these two orange marbles. So when you are assigning random variables, you should also not distinguish these two. You should always map to the same number. If you map these two at a different number, you can always construct a sigma a Borel set around the first map, and then the pre-image will only contain this, which is not in the sigma algebra. So to be able to make it a valid random variable, let's map it this also to 1. Okay. In that case, if you take this set, no outcome maps to this, so this is just empty set, which is also in the sigma algebra. And if you take this, you will get a pre-image will be these two outcomes. So the pre-image will be this set, which is there in the sigma algebra. There's no way you can create a Borel set here which will separate these two out because of the mapping you have taken. So this new random function would be a random variable. So one thing to notice here in general, although there is a complete a formal way to prove random variables where something some function is a random variable or not, there is one intuitive way to understand that if random variable is such that it distinguishes two outcomes which are not distinguishable in the sigma algebra, then it will not be a random variable. Random variable should not distinguish between two outcomes which are not distinguishable in F. Okay, one last thing to also notice that it is not required that random variable distinguishes all outcomes which are distinguishable in the F. Okay, so I would say it again. It is necessary that random variable does not distinguish two outcomes which are not distinguishable in F. Okay, if it distinguish two random variables, two outcomes which are non-distinguishable in F, then it will not be a random variable. However, the opposite is not true. It doesn't have to distinguish all outcomes which are distinguishable in F. For example, in this sigma algebra, green and red marbles are distinguishable. But here, if I assign green also to 1, I am not distinguishing between orange and green. This will still be a random variable because you can see now two maps pre-image would also be 5, pre-image of 3 will also be 5, and the pre-image of 1 would be complete omega because it will all outcomes maps to this, and this omega is still in the sigma algebra. So that is completely fine, right? And you can formally understand this. If two events are distinguishable in this, then of course their union will also be there in the sigma algebra. So if you map to them in the same number, then the pre-image would be the union of these two outcomes, and that will also be in the sigma algebra. So what is the probability law of a random variable? So we assume that we have already defined, so we have a omega sample space, we have a sigma algebra, and we assume we have already defined the probability measure on it. So we have a complete probability space, omega f p. Now we have defined a random variable x, which maps outcomes to the real line, and we have also made sure that if you take any Borel set, the pre-image is also in F. Now the question is, the Borel real line has a sigma algebra, which is Borel sigma algebra, which is also a set is a sigma algebra. So it is possible to measure the sets in this sigma algebra. So can we assign a probability measure to these sets in a consistent way? What do I mean by consistent way? So let us see this. Our goal is to assign a probability measure to the sigma algebra. So we notice first that if B is a Borel set, then X inverse B, which is a pre-image, is defined by a set of all outcomes which maps to an element in B. So X inverse B is an event and it is in sigma algebra because of the definition of random variables. So because it is in F, then its probability is known, right? Because if suppose the X inverse B is some set E, then we know the probability of E because it is in sigma algebra. So X inverse B represents an event E with probability P of X inverse B. Okay, and this probability is defined because X inverse B is in F. So now we say the probability law of X is defined as, which we denote as P subscript X B. So Px is the new measure which is defined for every possible Borel set in Borel sigma algebra, and we say that Pxb is equal to probability of the pre-image of B. Okay, it's the probability of the set of all outcomes which maps to elements in B. So this is nothing but the pre-image of B. So what I'm saying is that the probability, if you take any Borel set, so if you take Borel sigma algebra, I can define the probability measure in this way, that you take a Borel set, the probability of this Borel set would be equal to the probability of its pre-image, and that we have already defined. So that there is no issue in there. This new measure is known as the probability law of the random variable. And if you change the random variable, this probability law will change. So this is specific to a random variable. So we sometimes even say it in shortcut, we say it's the probability of X belongs to B. Okay, this is the probability that the random variable takes value inside B. But what we actually want to say that this is the probability that the event, sorry, the probability that the probability of the occurring of the pre-image of this Borel set. Okay. So how are they same? You can see X is not X is X omega. So when I say X omega is in B, it means the random variable takes value inside B. And when and I am interested in the probability of this. So when will X omega takes value in B? When there is an omega such that it is mapped inside B, so that X omega is in B. Okay, so this is same as saying that it is a probability of that omega is in omega. It is a probability of omega such that sorry, just that X omega is in B. Okay, or omega is in X inverse B. So this is the probability of X inverse of B. Right, let us take an example. We have considered a coin toss, so capital omega is ht, and random variable we have taken in a way that h is mapped to 1 and t is mapped to 2. We have taken the complete sigma algebra, so there is no issue of saying that is valid random variable or not. And then the probability measure is defined in this way that the probability of h is 1 by 4 and the probability of the singleton set T is 3 by 4. Okay, and then probability of phi is 0 and probability of capital omega is 1. That's automatic. So we have defined it for every element of sigma algebra. Now what we do is we take a specific bx of the form minus infinity to x, and let us see what will be the probability measure of those. Okay, so if x is minus 10, the bx is minus 20 to minus 10, then x inverse bx is 5. So the probability of px of this bx is nothing but the probability of the x inverse of bx, and x inverse is 5. So this will be equal to probability of 5. Okay, p of 5, and p of 5 is 0. Similarly, if you take 0.9, you get the same answer. If you take 1.01, then you have minus infinity to 1.01. Okay, so there is a typo here. It should be a plus. So this is Bx is also, these are Bx, not B. So these are Bx is equal to minus infinity 2 plus 1, 0.01. So x inverse is just H, set of H. So probability of Bx would be equal to probability of H, which is 1 by 4. Okay. Similarly, probability 1.9 you take, the inverse image is still H. So probability law of Bx is 1 by 4. Similarly, if you take 2.02, X inverse B is complete sigma space. So probability of this Bx for X equal to 2.02, this will be probability of capital omega, which will be 1. Okay. So specifically we say probability law of Bx, yeah, or probability of Bx sometime in this way. Okay, so can we write formally for every possible value of x? We can say that probability or a law of minus infinity comma x is equal to 0 if x is less than 1. It is 1 by 4 if x is between 2 and 1, including 1, and 1 if x is greater than or equal to 2. So this is for all possible values of x. I have defined this probability law for a set of the form minus infinity to x. So we have defined the probability law of this random variable in the last class. So we have defined it only for a particular Borel sets of the form minus infinity to x. Now is once we know this, can we define it for other sets? For example, so this is the definition of probability law, that probability law Px of B is equal to probability of set of made from all outcomes which maps to this set B, or such that x omega is in B. Okay, this is also equal to probability of x inverse B, where x inverse is the pre-image of B. So if I ask you what is Px of this set, 0.2 and to 1.5. So you have to calculate all omega which maps to this set. So does for h, does x omega xh belongs to this? So for h, xh is 1, which belongs to this set. So pre-image will contain h. Same with t. Does the xt belongs to b? Xt is 2. It does not belong to this set. So the only outcomes which for which map to this set are h. So the probability x of this set will be equal to probability of the singleton set h, which is 1 by 4. Similarly, what will be the probability of 1.2 to 1.5? Right. You can see 1 is not included in this set, 2 is also not included in this set. So the set which maps to the set of outcomes which maps to this set is empty. So the probability law of this set would be 0. Similarly, what is a px of 1? So this includes 1. This is just a singleton set which has 1. So x maps to this. So the pre-image would be singleton set H. So probability of x of this set would be 1 by 4. Okay, and then you can calculate even for countable. If you are given a set like 0.2 to 0.3 and 0.7 to 0.8 union of these two. Same way you can compute. You have to just compute pre-image, and then you have to compute the apply the probability measure on this pre-image to get the probability. So for any Borel set, we can get the probability law of this under this probability law. So we have assigned a probability law. Okay, now I want to visit this definition once again. We have said that only minus infinity to x is sufficient if you want to show that random variable, a function is a random variable. Right. What the definition actually says that for any Borel set, you have to prove that the pre-image of this Borel set is in F. Okay, and then we gave a shortcut that you have to, if you only show for many of the Borel sets of this form minus infinity to x, then it should be sufficient. So why it is sufficient? See, now we understand this, that every Borel set can be written as a countable union or intersection of sets of the form minus infinity to x or their complements. Okay, so this you can convince yourself because Borel set is made from open intervals. Okay, and sorry, Borel said the basic element was open intervals, and then you take all countable union and intersection of it to construct the Borel algebra, and then you say that this Borel algebra will contain all forms of closed sets, semi-open sets, the unions of these sets in this form. Okay, so we say that if you also make it in the form that this intersection, this will also work, right? So how is this? Let's see, 2 comma 3, right? How can you represent a set 2 comma 3 in the this form? Okay, so you can take a set minus infinity to 2, okay, and then if you take a set, okay, so this is minus infinity to 2, that is one set, okay, and if you take a complement of it, it will be from open set of 2 to infinity. Okay, if you take this bx b2 minus infinity to 2, which is closed from 2, and you take a complement of it, so you get open 2 to infinity, which is open from 2, and then you take another set b3, which is from minus infinity to 3. Okay, then you take a intersection of this, you will get minus 2 to, sorry, 2 to 3, and it's open from 2 and closed from 3 sides. So you get semi-open sets. Semi-open set, which is open from 2 and closed from 3. Okay, so these are Borel algebras, right? If once you can say that all this interval can be written in this combination. Okay, and the rest of the sets we have already shown that in Borel algebra, rest of the sets are nothing but just countable union of sets of this semi-open sets. And so every semi-open set you can represent in terms of the intersection of the complement or the of bx and bx. So from this, you can show that every Borel set can be written as a countable union or intersection of sets of the form Bx. Okay. Now we have shown that for any x, the pre-image of Bx belongs to F. Okay. From this, how can we prove that for any B, x inverse will be in F? Okay, that we have to prove that for every Borel set B, the x inverse of B should be in F. And what we have proved is that for every possible x, the set pre-image of the sets in the form Bx are in F. So two important results will be useful here to prove this. One is we will show that if x inverse in A, then x inverse of A complement is also in F. Okay, sorry, if x inverse A is in F, then x inverse of A complement is also in F. This means that if a pre-image of A is in F, then the pre-image of A complement is also in sigma algebra. Okay, how do we prove this? So x inverse of A complement is made from all outcomes which maps to this set. So formally we can say x inverse of A complement is set of all omega such that x omega is a member of A complement. Okay, and if x omega is a member of A complement, it means x omega is not a member of A. Okay, because A and A complement are disjoint. So if x omega is not in A complement, then x omega will be in A. Okay, so this is a set of all omega such that x omega is not in A. Okay, this means it is a complement of the set of all omega where x omega is in it. Right? Can you convince yourself? So first set, this one is a set of all omega so that x omega is not in A. And this set is the set of all omega so that x omega is in A. So if you make a set where x omega is in A and you take the complement of this, then you get all omega where x omega is not in A. So these two sets are same. Okay, so and this middle set is nothing but the pre-image of A. So this is the pre-image of A complement. So x inverse of A complement is nothing but the complement of the x inverse. Okay, now we have proved that x inverse A is in F. So the complement of this set will also be in F because it is sigma algebra. So that's why x inverse A complement is also in the sigma algebra. So if this is, because this is equal to this means X inverse of the A complement is also in sigma algebra. Okay. Similarly, you can show that if X inverse of A is in F and X inverse of B is in F, then X inverse of A union B is also in F. Okay, you can write the same argument in the same way, and you can prove that. You can construct the set of all omega and prove this. Similarly, you can also say that if the pre-image of A and B belongs to F, then the pre-image of A intersection B also belongs to F. And this you can also extend for countable unions in the same fashion. Okay, so from these three results, you can see that if Bx is in sigma algebra, then its complement will also be in sigma algebra. It's all countable union or intersection of these complements and the sets of Bx form will also be in the sigma algebra. Okay, and we have already proved that Bx belongs to a sigma algebra. And then once we know that, then we know that all such sets will also be in the sigma algebra. Okay, and this included with the argument that every Borel set can be written in this form completes the proof, right? So every Borel set can be written in this form, and then you can show that this form does belongs to the sigma algebra if all Bx belongs to sigma algebra. So this means just proving that Bx belongs to sigma algebra is sufficient. If you can prove this, then it's automatically that all for every Borel set, it will be in the sigma algebra.